Hello students. Today's lecture is in continuation with the previous lecture related on the topic laminar forced convection through pipe. Let me briefly revise what we have previously done and then we'll move forward. Uh, in the previous lecture, we considered a laminar flow of an incompressible Newtonian fluid through a circular pipe under the action of pressure gradient, and the velocity distribution was Vz, which was twice the average velocity into 1 minus r by capital R whole square, and this was the pipe system through which the fluid moves from up to down. Now as the fluid moves in the downward direction, there is a change in the temperature profile because of the heating of the fluid which is done in this pipe. Now the heating is carried under two boundary conditions. One is constant wall temperature conditions and the other was constant heat flux conditions. So based upon these two boundary conditions and plus based upon the one more additional condition, that Peclet number was considered to be much greater than 1. That is, convective flux is much higher than the molecular flux, and based upon this condition we had a basic equation which was rho Cp Vz and del T by del Z equal to K by del R into R dt by dr. That is, the convection part in the Z direction was considered equivalent to the conduction part which is occurring in the radial direction. Now based upon this main equation and using the boundary conditions of constant wall temperature and constant heat flux condition, we determine the temperature distribution profiles. Now temperature distribution profile for constant wall temperature was Tb out equal to Tw minus Tb in exponential of minus pi d h over m dot Cp into L, where Tb represents basically the bulk temperature and Tb in is the bulk temperature of the fluid which is at the inlet of the pipe, and Tb out is the bulk temperature of the fluid at the exit conditions. So this was the temperature profile which we determined, and we also studied that this is basically varies exponentially along the length of the pipe. Then the second boundary condition was constant heat flux conditions, where the outside of the pipe is wrapped around with an electrical wire and a constant temperature and constant voltage is given, which will give us constant heat flux throughout the length of the pipe, and Tb out and the temperature profile basically is given by this expression, that is Tb out is Tb in plus pi d kilowatt over m dot Cp L. That is, the temperature variation is basically a linear profile in constant heat flux condition. This is what we derived in the previous lecture. Now based upon these derivations, now what we're going to do is we're going to modify these expressions of temperature distributions for both the boundary conditions in terms of dimensionless numbers. Because sometimes there are, while giving some entrance exams, you come across such similar questions, but then the options, they are represented in terms of dimensionless terms. So then you get confused how to, we didn't derive such things. So they are very easy. You can convert these expressions in terms of your dimensionless numbers. So in order to convert them, we'll be requiring few basic dimensionless terms. One is Nusselt number. Now, what is Nusselt number? Nusselt number is basically represented as hd by k. Second dimensionless term which we'll be dealing with is Reynolds number, which is dv rho by mu. And the third dimensionless number we'll be dealing with is Prandtl number, that is Cp mu by k. Now, since the flow is laminar, so we'll be dealing with Reynolds number, plus since there is a variation in the physical properties of the fluid because of the variation in the temperature, so Prandtl number will account for that. And then obviously there's a heat transfer occurring, so Nusselt number will be dealing with that. So the temperature profile which we have written over here, that is for constant wall temperature and constant heat flux temperatures profile, will be rewriting them in terms of these three dimensionless numbers. So let's first start with constant wall temperature. Now, constant wall temperature, we said that at constant wall temperature, that is the temperature profile over the entire length was represented as Tb out as Tw minus, I'm actually rewriting the same expression, over m dot Cp. Clear? Now, Nusselt number we have defined over here, Reynolds number and Prandtl number we have defined over here. Now, let's take what is Nusselt number by Reynolds number into Prandtl number. That will be basically hd by k into dv rho by mu, that is the reciprocal of the Reynolds number, and the reciprocal of the Prandtl number, that is, now this k gets cancelled with this, viscosity d will cancel with this, so it finally comes out to be v rho into Cp, right? So that is Nusselt number over Reynolds number into Prandtl is h by v rho Cp. Now, what is mass flow rate? Mass flow rate is volumetric flow rate into density. Now, volumetric flow rate can be written as velocity into area into density. Now, what will be velocity into density? That will be mass flow rate by the area. So that is mass flow rate by pi by 4 d square. So we can replace this expression over here. So this term will be written as h pi d square by 4 mass flow rate into Cp, right? Further, so now Nusselt number by Reynolds number into Prandtl number is h pi d square by 4 mass flow rate Cp. Now multiply both sides by L by d. So multiplying both sides by L by d. So what do we have is, and this d cancels up with this d, and we shift this 4 over here. So what we have is 4 into Nusselt number by Reynolds into Prandtl into L by d, which is nothing but we have h pi dl by m dot Cp. And where is this term occurring? It occurs over here. So simply replace this expression that is this expression over here, by this term. So your expression finally comes out to be Tb out as Tw minus Tb in exponential of minus 4 Nusselt number by Reynolds into Prandtl into L by D. So that's the another way of representing your temperature distribution in terms of dimensionless number. Clear? Now for heat flux, constant heat flux conditions, Tb out was Tb in plus pi dq mcp into L. Right. Now for this, if we multiply Reynolds into Prandtl, we'll have Tv rho by mu into Cp mu by K. Now this mu gets cancelled with this. So we have dV rho Cp by K. And multiplying both sides by pi d by 4. Multiplying both sides by pi d by 4. So what do we have over here? We have pi d Reynolds number Prandtl number by 4 equal to pi d square by 4 into V rho Cp by K. And what is this entire thing? That is m Cp by K. Right. So find out mcp in terms of Reynolds into this and then substitute back over here. Now what will be mcp from here? Mcp will be pi dre pr by 4 into k. Substitute back in this expression. So what you have is Tb out as Tb in plus 4 q L by K Reynolds number into Prandtl number. So this is the expression for temperature distribution of constant heat flux in terms of dimensionless numbers. Clear? So that's basically the another way of representing the temperature distributions. Now moving further, now we're going to calculate the Nusselt number for thermally developed flow. The Nusselt number for thermally developed flow. Now why we are calculating Nusselt number? Because this Nusselt number will be expressed in will be having a certain value for both the boundary conditions, that is for constant wall temperature as well as constant heat flux condition, and that value is very important from designing of equipment point of view. Either it's designing of your heat exchangers or designing of your evaporators. Now let me ask you a very simple question. Do you know the value of Nusselt number for laminar flow flowing in a pipe under constant wall temperature conditions or under constant heat flux condition? What's the minimum value of Nusselt number? If you do not know, let's find it out. Now for this, let's first consider the constant heat flux situation, constant heat flux situation, and we're going to find out the minimum value of Nusselt number for laminar flow of fluid flowing in a pipe. You must be familiar with that value, but currently if you're not able to recognize how much is that value, let's find it out. Now for this, let's revise what we have done previously. That in the introduction, like at the start of the lecture, I've told you we'll be dealing with this equation. That is, at the start of the deriving this temperature profile, we said that we'll be considering the Peclet number much greater than 1. That is, the convective flux is much greater than your molecular flux. So using this equation, I'll rewrite that equation again. That is rho Cp Vz del T by del Z equal to K by R del R into R dt by dr. And further, this velocity expression which we are using is twice of average velocity into 1 minus R by capital R whole square. Now simply replace this velocity expression by this term. So what we have is 2 rho Cp, your average velocity, into 1 minus R by capital R whole square into del T by del Z equal to K by R del R into R del T by del R. Now for constant heat flux condition, we derived in the previous lecture, that is del T by del Z is nothing but pi d Kw by m dot Cp, and that is basically a constant. So this expression can be written as pi d Kw by now mass flow rate. Mass flow rate is basically your volumetric flow rate into density, and volumetric flow rate is your average velocity into the cross sectional area. So mass flow rate will be replaced by density into average velocity into area into Cp. Now simply substitute the value of dt by dz, that is this thing, over here in terms of this thing. Further, now Nusselt number is hd by k, we all know. Now heat transfer coefficient is basically your flux divided by the temperature difference into d by k. So that is Qwd can be written as k into Nusselt number into Tw minus Tb. Now where is Kwd occurring? Kwd is occurring over here. So finally your dt by dz, which was in terms of this expression, and in this expression we have simply replaced d into Kw as in terms of your Nusselt number. So substituting all these expression in this main equation, that is this thing, will finally be left with, okay, let me substitute and then let's see what terms gets cancelled up. So 2 rho Cp into average velocity into 1 minus R square by this thing, we have pi k Nusselt number Tw minus Tb over rho average velocity pi r square Cp equal to k by r del by del r del t by del r. Now you see there are some terms which gets cancelled up. Rho gets cancelled up with rho, average velocity with average velocity, thermal conductivity, Cp gets cancelled out. Cp, what else? That's it. So finally we are left with 2 by r square 1 minus r by r whole square Nusselt number Tw minus Tb equal to 1 by r del by del r del t by del r. We are left with this expression. Now, in order to solve this thing, in order to calculate the value of Nusselt number, what we're going to do is we will introduce a dimensionless variable, that is theta as nothing but ratio of t minus tb by tw minus tb, and zeta equal to small r by capital R. We're going to convert this main equation in terms of dimensionless variables, that is theta and zeta. Theta is the ratio of the temperature terms and zeta is ratio of r by capital R. So simply convert your main expression in terms of dimensionless. So that will be 2 by r square 1 minus zeta square Nusselt number Tw minus Tb. Okay, now r, small r, can be replaced as capital R into zeta del r. So that will be r into del zeta by del r zeta t. What is t from here? That will be Tw minus t into theta. And if you differentiate dt, so you will be differentiating del theta, keeping the other terms as constant. So Tw minus Tb is out. So we have del theta over here, and del r is nothing but r del theta. That is this thing. Now if you see Tw minus Tb gets cancelled up. This r gets cancelled up with this r. This 2r cancels with this r. So finally your equation reduces to into Nusselt number equal to 1 by zeta del by del zeta into zeta del theta by del zeta. Now let's talk about the boundary conditions. At r equal to capital R, that is at the wall, the temperature was Tw. So when T is Tw, what will be zeta? For zeta equal to 1, theta will be 1. At the center, at r equal to 0, the gradient was 0. So that means when zeta is 0, we have del theta by del theta as 0. So we're going to solve this equation with respect to these boundary conditions. So upon integrating, that is del theta by del theta zeta del theta by del zeta as twice 1 minus zeta square by Nusselt number. Now upon integrating, what we have is zeta del theta by del zeta into twice, we have zeta square by 2 minus zeta 4 by, okay, we have 1 minus zeta over here also, right? So shifted this zeta over here, this will become zeta and zeta cube, and then upon integrating, I'm writing that expression plus c1. Now using second boundary condition, that zeta equal to 0 del theta by del zeta is 0, which will lead to C1 as 0. So del z. So the expression becomes into Nusselt number. Now again, this 2 cancels with this zeta cancels with this. So del theta by del zeta reduces to zeta minus zeta cube by 2 into Nusselt number. Upon further integrating, we have theta as zeta square by 2 minus zeta 4 by 8 into Nusselt number plus C2. Now use the first boundary condition, that is theta is 1, theta is 1. That is zeta is 1, theta is 1, which will give me the value of C2. Now C2 comes out to be 1 minus 3 by 8, your Nusselt number. Now substituting this back in this equation, so we have theta as 1 minus Nusselt number by 8 into 3, 4 zeta square by zeta 4. So upon substituting, we have this expression. Clear? Let's name it as A. Moving further, now what is bulk temperature? We defined in the previous lecture. Bulk temperature was 0 to 2 pi, 0 to r. It's Vz, T, R, dr, d theta by the volumetric flow rate, 0 to 2 pi Vz, r, dr, d theta. Clear? Or it can be also written as 0 to r Vz, T, R, dr over 0 to r Vz, r, dr. Clear? Now we're gonna rewrite this expression in terms of the dimensionless variables theta and zeta. So upon writing, now what will be theta b? Okay, before that, now what is theta? Theta is t minus tb by tw minus tb. What will be theta b? For that, t will be replaced by tb and this comes out to be 0. Clear? Right? That is bulk temperature in terms of dimensionless number, that is 0. And what is theta b? Basically it's your this expression in terms of dimensionless variables, this expression in terms of dimensionless variable, which is 0 to 1. I've already converted that expression of this expression in terms of dimensionless. You can also try simply replace t in terms of theta, r in terms of zeta, vz gets cancelled up. Okay, not vz gets cancelled up, the term in vz, that is 1 minus r by capital R, that will be replaced by 1 minus zeta square. So that is what I'm writing basically. So try to convert that, so you will be getting this expression. Clear? So what I've done is basically I've converted this bulk temperature in terms of dimensionless variable, and in dimensionless variable term bulk temperature is 0. That means this expression is 0. So what does it lead? It leads that the numerator part, that is equal to 0. Right? Now in this numerator term, we'll put the value of theta which we have calculated. That is this equation A. So substituting theta from equation A in equation B. So what do we have? We'll have this expression in terms of Nusselt number equal to 0. So let's replace theta. So 0 to 1, 1 minus zeta square into 1 minus Nusselt number by 8. I'm basically substituting the value of theta first. into zeta into this. Now let's try to integrate this term from 0 to 1 with respect to zeta and substitute the entire expression equal to 0. From there we will calculate the value of your Nusselt number. We're gonna get the value of your Nusselt number. Now try to integrate it very carefully and then put the limits zeta equal to 0 and zeta equal to 1. Now I've done the integration part. What after integration what I'm left with is this expression, that is zeta square by 2 minus Nusselt number by 8, 3 zeta square by 2 minus 4 zeta 4 by 4 plus zeta 6 by 6 minus zeta 4 by 4 plus Nusselt number by 8 into 3 zeta 4 by 4 minus 4 zeta 6 by 6 plus zeta 8 by 8, putting the limits 0 to 1 equal to 0. So very carefully try to integrate and get this expression. Now putting the values zeta 0 and the lower limit and the upper limit 0 to 1. So upon putting the limits, what I'm left with is 1 by 2 minus Nusselt number by 8, 3 by, that is finally upon putting the limits what I'm left with is 2 by 3 minus 1 by 4 plus Nusselt number by 8 into 5 by 24 equal to 0, and finally upon solving this term I have Nusselt number as 48 by 11. Now what is 48 by 11? 48 by 11 is 4.36. Now this you might be remembering 4.36. This is the minimum Nusselt number for a laminar fluid flowing in a pipe under constant wall temperature. Under constant heat flux conditions. Similarly, we can derive for constant wall temperature. Similarly, we can derive it for constant wall temperature. And for constant wall temperature, just remember that minimum Nusselt number is how much? Anyone? It's 3.66. So remember these two numbers. They are very, very important numbers. For constant heat flux, the Nusselt number is 4.36. For constant wall temperature, the Nusselt number is 3.66. Clear? Now, based upon these minimum numbers, there are many authors, many researchers, they have presented their own version of correlation of Nusselt number in terms of Reynolds number and Prandtl number, where all those correlations they basically reduce to these two specific values. Clear? Now you can try for constant wall temperature to determine the value of Nusselt number, that is 3.66. If anyone is interested, I can provide you the derivation of how to get this value of 3.66 for constant wall temperature. Clear? Now let's see some very important correlations available in literature. Now for laminar flow in a circular pipe, in a circular tube, for constant heat flux condition, the Nusselt number is 1.953 into L by D REPR raised to power 1 by 3 and it's 4.364 plus 0.0722 d REPR by L. This is valid when L by d REPR is less than 0.03, and this is valid when L d REPR is greater than or equal to 0.03. This expression for heat flux was derived or was proposed by Graetz, and he gave his number, that is Graetz number, that is nothing but it's a ratio of Reynolds Prandtl into d by L. He proposed this dimensionless number as Graetz number. Clear? For constant heat flux, it is this thing. Now, if you see over here in this expression, if length approaches infinity for a very long tube, this Nusselt number approaches 4.36, which we have derived over here. Clear? Similarly, for constant wall temperature, Graetz proposed that Nusselt number is equal to 1.615 into L by d REPR raised to power minus 1 by 3 minus 0.7, where this is valid for L by d REPR less than or equal to 0.005, or Nusselt number is equal to 1.615 L by d REPR minus 1 by 3 minus 0.2 for a range of 0.005 L by d REPR up till 0.03, and it's equal to 3.66 plus 0.0499 d REPR by L for this ratio greater than 0.03. So depending upon this ratio, depending upon the Graetz number, so he proposed Nusselt number, three different correlations for Nusselt number for prediction of Nusselt number under constant wall temperature conditions. Clear? Then in 1990s, this was the Graetz, the very first scientist who proposed the correlation for Nusselt number. Then in 1996, Tate proposed his version of correlation, which was Nusselt number as 1.86, Reynolds number, Prandtl number, d by L 1 by 3 as mu b by mu s raised to power 0.14. But this is valid for this condition that Prandtl number ranges between 0.48 to 16,700 and mu b by mu s is in between 0.004 up till 9.75. Now what is this mu b by mu s? Now this is basically an empirical correction factor which takes into account the effect of temperature variation on the thermophysical properties of the fluid. So it's a correction factor. Clear? So then it's a very well known equation for laminar flow for both heat flux as well as for both constant wall temperature conditions. The results are basically approximately the same, plus minus 25%. Either you can use it in constant wall temperature conditions, or either you can use it in constant heat flux conditions. Then in 1993, 1983, sorry, 1983, Hausen proposed another correlation for Nusselt number prediction, and that is Nusselt number is 3.66 plus 0.668 Reynolds Prandtl d by L over 1 plus 0.045 Reynolds Prandtl d by L 0.66 into mu b by mu s as 0.14. Now this is valid for this condition that Reynolds number Prandtl by d by L is in the range of 100 to 1500. This was proposed by Hausen equation. Clear? Now both these equations are valid for all these three equations, that is Graetz equation, Cesar-Tate and Hauss equation. They are for laminar flow conditions. Now if we consider the turbulent conditions, for turbulent conditions, the very commonly known correlation for prediction of Nusselt number for turbulent conditions, for constant wall temperature or for constant heat flux conditions. Anyone? Any idea? Yes, it's Detrius Boltus equation. It was proposed in 1930, and it is Nusselt number is 0.023, Reynolds number is 0.8, and Prandtl number is n, where n is 0.4 subject to condition that surface temperature is greater than Tb, that is your heating, and n is 0.3 for Ts less than Tb, that is cooling conditions. Now again this equation gives the result in the range of plus minus 20% for both constant wall temperature and constant heat flux conditions. So depending on either boundary condition, you can use this expression for Richter Boltus, but subject to condition that this equation is valid for Prandtl number in the range of 0.5 to 120, Reynolds number in the range of 6000 to 10 raised to power 7000, and L by D should be greater than 60. Then in 1936 again, Cesar-Tate proposed his correlation for turbulent flow, that is Nusselt number is 0.027, Reynolds number 0.8, Prandtl 1 by 3 into mu b by mu s raised to power 0.4, 0.14, sorry, 0.14. Now this correlation is used in plus minus 10% for constant wall temperature and constant heat flux condition results, subject to condition that the Prandtl number is in the range of 0.7 to 10,000, and Reynolds number again in the range of 6,000 to 10 raised to power 7, and L by D should be greater than 60. Clear? Then there is another correlation for turbulent flow condition that was proposed in 1970 by Pitikov. Pitikov-Pop equation. Now this equation uses a very important term, that is friction factor. The friction factor of a fluid which is flowing in a pipe. So Nusselt number is proposed as F by 8 into Reynolds number into Prandtl over K1 plus K2 into F by 8 1 half and Prandtl number 2/3 of -1, where K1 is 1 plus 3.4 times of F K2 is 11.7, 1.8 of Prandtl 1 by 3, and friction factor is 1.82 log to the base 10 of Reynolds number minus 1.64 raised to power minus half. But this condition is valid for Prandtl number in a range of zero point 0.5 to 2000, but Reynolds number is in the range of 10 raised to power 4 to 10 raised to power 6. So that's why for Reynolds number less than 10 raised to power 4, this equation is not valid. So over there, we're normally going to go for your Dittrich-Poultice equation. But this equation in this range behaves in a similar way as that of your Dittrich-Poultice equation. Clear? So these are the few correlations for both laminar and turbulent conditions under constant wall temperature and constant heat flux condition for a fluid flowing in a pipe. Clear? Now let's try to solve a very simple question, very simple numerical. Okay, now the question is as follows. The water is flowing through a pipe whose internal diameter is 5 centimeter with an average velocity of 0.01 meter per second. I again repeat, water is flowing through a pipe whose internal diameter is 5 centimeter with a velocity of 0.01 meter per second. Now we need to determine the length of the pipe so as to increase the temperature of water from 20 degrees Celsius to 60 degrees Celsius. Again repeat, we need to determine the length of the pipe so as to increase the temperature of the water from 20 degree to 60 degree under following conditions. First condition is your constant wall temperature condition, that is there is a steam condensed on the outer surface of the pipe. Steam is condensed on the outer surface of the pipe so as to keep the surface temperature at 100 degrees Celsius. So as to keep the surface temperature at 100 degrees Celsius, that is TW is 100 degree. And second condition is constant heat flux condition, that is electrical wire is wrapped around the outer surface of the pipe so as to provide constant heat flux, that is Q, which is 1500 watt per meter square. Clear? So we have two boundary conditions. We need to determine the length of the pipe under both these conditions so that the temperature of the water increases from 20 to 60 degree and the pipe dimension is given and the velocity of the fluid is given. Now since the velocity is 0.01, uh, the flow is laminar, but still we can determine that by calculating the Reynolds number. Now since the fluid which will be entering into this pipe is at 20, the leaving it will be at 60. So let's take the roughly the average, the bulk temperature, the mean bulk temperature of roughly around 40 degree, because 20 60 roughly 40 degree. So at 40 degree the thermophysical properties of water is the density is 9 to 92 kg per meter cube. Viscosity is roughly around 654 into 10 raised to power minus 6 kg meter per second. Thermal conductivity is roughly around 632 10 raised to power minus 3 watt meter per Kelvin, and the Prandtl number is Cp mu by K, that is roughly 4.32. So based upon the bulk mean temperature, that is 40 degree, the thermophysical properties of the fluid is given. Clear? Now there are certain assumption. We assume that this system is under steady state condition and flow is fully developed and thermally developed. The flow is hydrodynamically developed and thermally fully developed. Clear? Now let's first calculate the Reynolds number, that is dv rho by mu. We know the diameter, we know the velocity, the property values of the fluid. So this comes out to be roughly 758. So that means yes, the flow is laminar. Done. Now part A, wall temperature conditions. Now wall temperature conditions, the profile TB out is TW minus TB in exponential of, we have minus 4 Nusselt DREPR into L. So from here we can calculate the length, because we know TB out, we know the wall temperature, we know Nusselt number, we know Reynolds number, Prandtl number, and D. Clear? So based upon all these terms, we can calculate your. Now Nusselt number we do not know. How do we calculate Nusselt number? Now Nusselt number for constant wall temperature condition, how much? 3.66. So everything is given, put the values, calculate the length. So length comes out to be 7.8 meters. Part B, constant heat flux condition, temperature profile. We derived, here it is, then I forgot. Yeah, temperature profile for constant heat flux. TB out is TB in plus 4Q L by K RE and PR. So all the temperature terms are given, all the conditions are given. Put it over there and calculate your length. So the length comes out to be how much? Should come out to be 13.8. You can clearly see, for in order to increase the temperature of a fluid which is flowing at these conditions in this pipe from 20 degree to 60 degree, the length under constant wall temperature is 7.8. But if we change the boundary condition, the length increases to 13.8. So from designing point of view, if you compare both the boundary conditions, we'll normally prefer to go for constant wall temperature conditions. But then if you are working at steam at very high temperatures, at superheated steam, so those superheated steams are very harmful. So over there we can prefer constant heat flux condition, but then you need to change the dimensions, the geometry of your heat transfer equipment for the same set of operations. Clear? So this is a very simple basic example dealing with your heat flux and wall temperature conditions. So that finishes up with the laminar flow of forced convection through pipe. Thank you.